Taylor's theorem. Now let's say we have a function f of x which can be expanded in powers of h, and the expansion be differentiable any number of times. Then f of x plus h is equal to f of x plus h times f prime of x plus h square f double prime of x by 2 factorial plus h cube third derivative of f by 3 factorial and so on. Now let's see how to prove it. Now let f of x plus h be equal to a naught plus a1h plus a2h square plus a3h cube plus a4h4 plus and dot dot dot. Now here a0, a1, a2 etc. are functions of x alone. Okay, so f of x plus h prime. So let's take the derivative, first derivative. So this disappears. We are left with a1 plus 2a2h plus 3a3h square plus 4a4h cube and so on. Let's differentiate it once more. X plus h is equal to, this disappears, so 2a2 plus 3 times 2a3h plus 4 times 3a4h and so on. Okay, let's differentiate it again. X plus h is equal to, this disappears again, so 3 times 2 times a3 plus, no, here h will not be there, this should be h square. Okay, so this will be 4 times 3 times 2 a4h and so on, and we can keep differentiating like that. Now let h is equal to 0. Now if we make h equal to 0, what happens? If you notice here, except the first, all the terms disappears. Except the first term, all the terms disappear. Except the first term, all the terms disappear, right? So f of x plus h would become a naught. F prime of x plus h is equal to a1. F double prime of x plus h is equal to 2a2. F third derivative x plus h would be 3 times 2 times a3 and so on. Now this basically implies a naught is equal to f of x plus h. This implies a1 is equal to f prime of x plus h. This implies a2 is equal to f double prime of x plus h by 2. This is a3 is equal to third derivative of x of f by 3 times 2. So we can make this as factorial and this as factorial. So which means our function, this one, we can now do substitution again and get f of x plus h is equal to f of x, because a naught is equal to f of x, plus h times f prime of x plus h square, f double prime of x by 2 factorial plus h cube f triple prime of x by 3 factorial and so on. Okay, now here let's try out a few things. Let x is equal to a. F of a plus h becomes f of a plus h times f prime of a plus h square f double prime of a by 2 factorial plus h cube f triple prime of a of the function f of a 3 factorial and so on. Pretty straightforward. Instead of x we are just saying a. Now let's put a is equal to 0 and h is equal to x. F of 0 plus x is equal to f of 0 plus h is what? X. F prime of 0 plus x square f double prime of a, which is 0 now, by 2 factorial plus x cube f triple prime of f of 0 by 3 factorial. So basically the function at x equal to some value. And if you remember from our previous session, this is nothing but Maclaurin's theorem, right? Okay, now let's do another thing. Let's put h is equal to x minus a. So what happens? This becomes, remember, it is f of a plus h, a plus x minus a. So a gets cancelled, we are left with f of x. This would be equal to what? F of a plus x minus a times f prime of a plus x minus a square f double prime of f of a by 2 factorial plus x minus a cube third derivative of f of a by 3 factorial and so on. Yes, so just by putting the appropriate values we are able to manipulate this entire theorem. Okay, now let's see how does this help. Let's say we have a function y is equal to f of x equal to log of sine of x, and we want to expand in powers of x minus 2. Okay, we have f of x is equal to log of sine of x. Now remember, we want this in terms of x minus 2. So which means in case of x plus h, we want the h to be x minus 2, right? So let's make this as x minus 2 plus 2. X we have minus 2 plus 2. And now let's move it around so that it becomes 2 plus x minus 2, right? So this becomes h, this becomes a. So f of a, which means 2. So f of 2 is equal to log of sine of 2. F prime of 2 is 1 by sine 2 times cos 2, which is cot 2. Second derivative is minus cosec square of 2. Third derivative is 2 cosec square 2 cot 2 and so on. So as per Taylor's theorem, f of x would be log of sine of 2 plus x minus 2. Remember, this is h, and then f of a. So this is cot 2, then minus, right? So h square, so h square would be x minus 2 square cosec square 2 plus 2 times x minus 2 cube cosec square 2 cot 2 and so on, right? You see, the beauty of this is that by just following a simple rule, we are able to expand log of sine of x in terms of x minus 2, which is actually quite complicated. But to arrive at it using Taylor's theorem makes it very easy. Okay, let's look at the next one. F of x plus a is equal to log of x plus a. Now we want it in powers of x. Okay, so f of x plus a is equal to log of x plus a. We want it in terms of powers of x. We are interested in f of a is equal to log of a. Yes, so f prime of a is 1 by a. F second derivative is minus 1 by a square. Third derivative is 2 by a cube and so on. So our function log of x plus a becomes f of x. Remember, here we are talking in terms of a, so x times f prime of a is 1 by a plus x square by 2a square plus x cube by, now here by the way there is a negative sign, this is minus, plus x cube by 3 times 2a cube times 2. So this 2 and this 2 gets cancelled, and next again it will start with minus. So our log of x plus a is equal to f of a plus x by a minus x square by 2a square plus x cube by 3a cube and so on. See, once you are able to get up to 4 to 5 terms, then it forms a pattern and you can just keep taking it forward. Let's take the next one. Let's say f of x is equal to e to the power of x. Now the derivatives of e to the power of x is very straightforward, right? And we want it in terms of powers of x. So f of 0, remember f of x plus h or a plus h, if we start with that, then since we want this should become x, h should become x, a should become 0. So a would be 0 and h would be x. So f of 0 is e to the power of 0, which is 1. First derivative is again e to the power of 0 equal to 1. Second derivative is again 1. Third derivative is again 1, and this goes on. So our function f of x is equal to e to the power of x can be written as f of 0 plus, remember h is x, so x times f prime of 0 plus x square f double prime of 0 f of 0 by 2 factorial plus x cube third derivative by 3 factorial and so on. Now f of 0 is what? 1 plus x times f prime of 0 is 1 x square by 2 factorial f prime of 0 is 1 x cube by 3 factorial again 1. Okay, so it keeps on going. So e to the power of x is equal to this. Okay, fourth one, a slight variation of this. Instead of e to the power of x, it is a to the power of x. And again we want it in terms of x, in terms of powers of x. Now you might feel that this was e to the power of x was so simple, they should be also simple. Yeah, it would be simple if you know the derivatives of this. Let's see. F prime of x would be what? Now here I'll just do it. Y is equal to a to the power of x. Let's take the log of both the sides. So it becomes log of a, x log of a. Let's differentiate 1 by y dy by dx is equal to, this becomes log of a plus 0. So dy by dx is equal to y log y, y log a, y is a to the power of x log a. Okay, so this is a to the power of x log a. Similarly, if you do the next derivative, this is a to the power of x log square a. F third derivative is equal to ax log cube a. F fourth derivative is a to the power of x log 4a. Yes, so again f of a plus h, we want it in terms of x, powers of x. So this is x, this will become 0. Yes, so remember in Taylor's theorem f of a plus h, if we take a as 0, then it is nothing but Maclaurin's theorem. So here also it is Maclaurin's theorem. So f of x, because a has become 0, that's the thing. So f of x, which is equal to a to the power of x, can be written as f of 0 plus x f prime of 0 plus x square by 2 factorial f second derivative plus x cube by 3 factorial f third derivative at 0 and so on. So our series becomes f of 0 is 1 plus x log a plus x square by 2 factorial log square a plus x cube by 3 factorial log cube a and so on. Applying the theorem itself is very simple. The tricky part here is to be able to differentiate multiple times a given function. Sometimes it's very easy, sometimes it's a little bit more complicated. Okay, I think that's enough. Bye for now.